The chemical composition and microscopic structure of a solid will define the macroscopic properties of a material. Material, even if visually very similar, are microscopically very different. From afar, it is difficult, for example, to distinguish between cut glass, ice, and a diamond, but these three materials are completely different in properties and composition. First of all, materials can be divided in three main classes based on their properties: metals, ceramics, and polymers. We all have a clear everyday example in mind of these materials, but let's look at the properties more closely. Metals are made by a single type of metal atom or multiple ones, forming in that case alloys. They are chemically reactive in most cases. One example is to oxidation. They are very dense and conduce electricity and heat well. They are also, in some cases, magnetic. Mechanically, they are malleable and ductile, meaning that they can be made into sheets or wires very easily. Ceramics are the opposite. They are mostly made of metal oxides or nonmetals. They are chemically inert and they do not conduce heat and electricity well. They are light, porous, hard, and rigid, not flexible at all, very easy to break. The last main class of materials is polymers. Plastics are a good example of polymers. Plastics are mostly hydrocarbon-based, inert, so chemically not reactive, good insulants, and have a wide range of mechanical properties. Most plastics melt at very low temperatures when compared to other materials. Another parameter that we can use to distinguish materials is their degree of order. This is based on the crystallinity of a material. A crystal is a solid with a high degree of microscopic order, where the single atoms are always positioned in the same way, like in salt. On the other hand, if there is no microscopic order whatsoever, we have an amorphous solid, like glass. Of the materials that we discussed, metals and ceramics can show order and microstructure, while plastics generally don't. The most common crystal in our daily lives is cooking salt, sodium chloride. If we take a sodium and a chloride ions to form salt, we can repeat the two ions in the plane to form an ordered structure. We can then repeat the same ordered structure by overlapping different planes, forming an ionic crystal. It is easy to see that for sodium chloride we have a repetition of a Na and Cl. The unit cell of a crystal is going to be everything that is inside this cube. The unit cell is going to be repeated in space and is so small when compared to the real size of a crystal that we can consider it repeated infinitely. If there is no unit cell that is repeated throughout the solid, the material is amorphous. In this case, the distance between the atoms is not constant anymore. A good example is silicon dioxide. In its crystalline form, it is quartz crystal, where silicon and oxygen are connected with an hexagonal geometry in the plane. The network of covalent bonds is formed by having each silicon bonded to 4 oxygens in a tetrahedral geometry, and each oxygen bridging 2 different silicons. Quartz is formed by slow cooling of magma or from concentration of silicon dioxide-rich waters. In both cases, the key is that the process is very slow. When melted silicon dioxide is cooled down very quickly, and it will not have time to form a crystalline structure, it will form an amorphous glass. There are different ways to arrange atoms in a crystal. Let's take the example of metals, that in most cases form crystals that are made up of only one type of atom. We can imagine how these atoms could be arranged in the plane. In the first case, the atoms are one on top of each other. This means that each atom in the plane touches 4 other atoms in a square geometry. See the green atom as an example. It comes in contact with 4 atoms in the plane, blue. We call this coordination number 4. But what if we try to minimize the empty space? If we move each line by the radius of an atom, we see that the atoms are more compact, leaving less empty space. This is an hexagonal geometry, since each atom touches 6 other atoms in the plane. Now, If we overlap multiple layers, other atoms come in contact with a green atom. In the square geometry, the central atom touches two more atoms, one from the plane above and one from the plane under, for a total coordination number of 6. In the hexagonal geometry, instead, it touches 3 more atoms above and 3 more under, for a total coordination number of 12. The orientation of the layers define the geometry of the unit cell. For metals, the most common geometries are cubic, body-centered cubic, where we have one extra atom in the center of the unit cell, and face-centered cubic, where there is an extra atom in the center of each face of a cube. There are other and more complicated unit cells, such as hexagonal, which is also typical for metals, tetragonal, etc. We have seen crystals of metals, salts, and oxides. Crystals are not limited only to this. Also, organic molecules can crystallize, and even entire biomolecules, such as proteins, can be crystalline.